Hello and welcome. In today's topic, I'm going to talk about the silicon based semiconductors. From the space hardware to toasters, modern life depends upon silicon based semiconductors because they make the electronic devices smarter. But there has been a verge of deficit in silicon based semiconductors, and also we have hit a limitation of physics and energy density, wherein we can't go much smaller than what the current size is, which is, I believe, around 10 to the power of minus 8 to 10 to the power of minus 9, somewhere around this. We can't go beyond, be much smaller than this, and also the energy density cannot be improvised, which is the rate at which is functioning at the moment. Before we get into what is the replacement for this, let's try to understand what a silicon semiconductor is. It is the foundation of modern electronics and they are used in wide range of applications including computers, smartphones and other electronic devices. The silicon semiconductors work by the process called doping. So let's get back to the good old school days. So doping is to create a region of excess electrons, which is the N-type semiconductor, or deficit of electrons, which is the P-type semiconductor in silicon crystal. When the dope regions are brought to close proximity, they create a PN junction diode that can be used to control the flow of electricity. Silicon semiconductors have numerous advantages, including the high reliability, low cost, and other things which I'm not going to be exploring in this current video. Here, I'm going to focus about the limitations it has, such as the silicon has a relatively low melting point, which means it can only operate at a relatively low temperature. This limits its usage in the high temperature situations. And also because of the limited electronic mobility, which means that this is not efficient at conducting electricity as some other materials. It has a poor thermal conductivity, which means it doesn't dissipate heat well. This can be a problem in high power or high temperature applications where overheating can be an issue. And also silicon is relatively brittle and can be easily damaged, which can be a problem in some applications. And also the environment impact while creating a silicon based semiconductor is quite high. Overall, the silicon has been a very successful material for use in semiconductors. It has some limitations which I have discussed in the earlier points that might be addressed by using an alternative material called carbon nanotubes, which I'll be going to explore in the coming slide. In this slide, let's try to understand the use of carbon nanotubes. The carbon nanotubes have a number of properties that make them attractive to use in electronics and other applications, as a carbon nanotube is an allotrope that resembles a tube of carbon atoms. The carbon nanotubes are extremely robust and difficult to break, but they are still light. Because of their exceptional mechanical, electrical, and thermal properties, carbon nanotubes are one of the most investigated nanomaterials. There are few ways in which they are better in silicon semiconductor as well. Let's try to understand these aspects. Firstly, it has a higher electron mobility. The carbon nanotubes have a much higher electron mobility than silicon, which means they can conduct electricity more efficiently. This can result in faster and more efficient devices. It has better thermal conductivity, which means that it can dissipate heat more effectively. This can be very important in high power or high temperature applications where overheating can be a problem. And because of the smaller size, being carbon nanotubes are much smaller than silicon semiconductor, which means they'll be able to create smaller and more compact electronic devices. And also coming to the flexibility aspect of it, carbon nanotubes are much more flexible than silicon, which means they can be used in wide range of applications and can be easily integrated in flexible electronics. Overall, the carbon nanotubes have the potential to offer significant advantage over silicon semiconductors in a number of applications. However, it should be noted that carbon nanotubes is still at a very early stages of development and it remains to be widely adopted in the future until the primary premise is being accepted, which is the production, the electronic properties, the dispersion, and the health and the safety regards. If these aspects are met, then I'm pretty sure that the carbon nanotubes will be a breakthrough in the coming days to come.